Now, I'm going to turn on a light. Give us a little bit of light. I don't have fancy pictures, so when you buy a telescope, or when you're looking to buy a telescope, there's always numbers on your telescope. It don't matter whether it's a Newtonian, or it don't matter whether it's a compound telescope or a refractor. There's numbers on them. And there's usually a plate that'll tell you your aperture, your diameter or aperture. It'll tell you your focal length. Sometimes they use F, sometimes it's an F with a slash. That's actually your ratio, focal ratio. We're going to go through each of these as we go. You got a little AZ, that would be alt azimuth, which means the telescope goes side to side and up and down. What else we got? We got an HD, that's a high definition. That's we'll talk about that when it comes up. So the most important number on your telescope is the aperture. More aperture means more light. And you can figure that out by taking the diameter squared. And using that formula, you can see how if we go from a 200 millimeter telescope down to a 100 millimeter telescope, it becomes, we lose 4 times as much light. Now this is important because, yes, aperture is great, but aperture fever is not good. Portability makes a difference. Cost makes a difference. Will it fit in my car? Or do I have to take a minivan or a van? Or you'll end up with something like this. You imagine lugging that out to Dave's dream. Yeah. I'm sure it takes stunning images. The next number is focal length, and we need to know focal length because it helps with our figuring on our eyepieces and such. So the focal length, once the light goes through your primary lens, if you have a refractor, or if it hits your primary mirror, if you have a reflecting telescope, from that point to where it comes out to your eyepiece, that's the length, that's your focal length. So if we've got a refractor, the light's coming in the light shield here right now, and it hits the lens, and then it's focused to a point at the back of the telescope. So that's pretty straightforward. That's the focal length. In a Newtonian type of telescope or reflector, it comes in the front. There's nothing here. It comes in all the way to the mirror, a curved parabolic mirror. It's going to come out, hit a secondary mirror, and come out the end of the eyepiece. So we have to add this distance plus this distance is our total focal length. And in a catadioptric or a compound telescope, it comes through lenses first, focuses the light down to a mirror, that focuses it back up, hits another mirror, which focuses it back down the tube. So it's bending the light or back and forth. Yes? Prime focus. I've heard the prime focus photography where you just stick your camera in there, but I've never heard that. Yeah. With those type of telescopes, which basically we know them as Cassegrain telescopes, there are 2 basic kinds. There's the Schmidt Cassegrain and the Maksutov. The only real difference is in the corrector plate. The light comes in through your corrector plate up there, goes back, hits the mirror, comes back up, hits another mirror, and then comes back out the end. It's actually a curved, reverse curved mirror. On this Maksutov, or the Max here, it comes in, hits your primary mirror back, or your secondary mirror, your primary mirror back there, comes back out, and hits a mirror that's actually painted on the back of the lens. These scopes have a little bit longer focal lengths, and they have superior, well, said to be superior image quality when you're looking in them. The Schmidts, however, give a larger field of view. They're a lot better for people who want to do photography, and they are way more popular. They're cheaper to make, and they don't have this complicated corrector plate here on them. So most everybody, or most people I know, that they go with the Schmidts. And the new technology with a lot of those telescopes, it has that high definition, which actually flattens out that field a bit. All mirrors create coma, which means the stars on the outside of your mirror or the image you're looking at, they don't make perfect pinpoints. They often look like little comets, so they call them coma. And the new technology with the Smiths will flatten that out, which makes it great for when you're doing photography. You're going to get pinpoint images from your whole image.
The other thing I'll say with the Smith category, the collimation, everyone says it's easy. I don't find it easy, but it's really necessary.
Yeah.
Whereas a Mac, you really almost don't have to.
Yeah. And it's a sealed. So that light makes a nice perfect path all the way through, yeah, and doesn't get shot off halfway out here and come hitting the side of the barrel instead of the center. Okay. Yikes, the yerks. So that's a 40-inch refractor that has 62 feet of focal length. That's a beast. This is why it's important to not get aperture fever, too. Now that we know our focal length, we're able to determine the magnification we're using in our telescope. So after the light comes through, it makes this path down to our eyepiece. We stick an eyepiece in there with a number on it too. Well, that's the focal length of the eyepiece, not the magnification or anything. So we have to divide the focal length of the objective, or our primary source, to the eyepiece one. A lot of times this is just abbreviated F, large F, and a small f, but I wanted to make it clear here. So if I had a 1200 meter focal length and I put a 20 millimeter eyepiece in there, that gives me magnification of 60. You're going to need to know this because it's not on your eyepiece. You'll need to jot it in your notebooks to know what each of your eyepieces will give you for magnification. But say you wanted 100. Well, that's fairly simple too. You just take your 1200 and divide it by the 100, and it tells you, well, go get your 12 millimeter eyepiece if you want to magnify it by 100 times. So that's fairly straightforward. Any questions? This is not meant to be a real technical talk. So.
What was the number? Darker your viewing is going to be.
This is yep, coming right up.
Sorry.
No, that is very true, and that's why it's important to not get down too much emphasis on this magnification. Every telescope has a magnification range depending on the size of your aperture. And usually it's 2 times the aperture in millimeters. So if you had a 150 or a 6-inch scope, 150 millimeters would give you could go up to 300 power. You will rarely ever make it to 300 power because the atmosphere is going to mess you up. You'll be lucky, I'm going to say, to get to 200. And your minimum, you just take that 300 and divide it by 10. So your useful magnification is between 30 and 300. Now, on those exceptional nights and you're on the moon and it's rock solid, you probably could get really close to 300. The other thing about magnification, which Andrew was about to say, is that when you double your magnification, your image gets 4 times dimmer because the light has been spread out. So to go with a whole lot of magnification on a very faint object is not an advantage. It's better to keep a wide field if you're looking for a faint nebula or a galaxy. Although with a galaxy, it's small, you got to find the optimum magnification.
Where the mirror comes in. More important, more light.
Yes, more light, more gas. But how far do you go? Do you go again for your magnification? So now that we know that, we can figure out our focal ratio. We know our focal length, and we know the size of our aperture. So if we divide that, 750, this is my 6-inch scope, 750 by 150, that means it's a f5. Now the f5, you just say, well, that's a number. What does that mean? Every scope is different. Some of them are f10s, some of the Cassegrains might be f20s, f23s, or whatever, what have you. The narrower your field, the f15s are going to give you a smaller field but more magnification. You're going to get better detail, especially on planetary, like Jupiter or Mars or something, the longer focal length is going to give you better quality images than the f5. But the f5 is going to give you a nice, great, big image so you can see the whole of the Andromeda galaxy. An f15, you're probably going to be focused more near the center. Now you can Barlow some of this stuff to help you with that kind of a problem, but shorter focal lengths usually give you lower magnification, useful magnifications. Any questions on that? Was that clear?
Ted,
Yeah.
if you had a long focal ratio, you use focal reducer.
Yes, that would be one way.
Are you talking about focal reducers as well?
No, but that would be one way to change your focal length, basically. That's a good point. That probably should be in here. Field of view. Now this probably won't mean, I'll post the equations tomorrow on the internet too, if you didn't catch them here. The field of view, when you buy an eyepiece, it has a number on it. 68 degrees ultra wide is what that one there is. If you've got an old Plausill, which I have that I use as a workhorse, it's probably a 50. It might not even say on it. You might have to look it up in your manual or in the box if you haven't had the box that you bought it in. But if it doesn't say anything on it, it's probably 50 degree. And they go right on up to over 100, some of those new eyepieces. And of course, the cost goes right up and up and up with each of these eyepieces too. You can spend a lot of money. Spend as much on eyepieces as you can your telescope. So it says it's going to show 68 degrees, but the magnification will change that. So let's just take an example. I've got a Plausill that says 50. I'm using 50 power. I should be able to see 1 degree of sky. Unfortunately, the Andromeda is probably about 1.5 or 2 degrees actually in full size. So I'd even have to go a lower magnification than that if I want to see the whole of it. But if I was to bump it up to 100, I'd only get a half a degree field of view. And this would only really be important. Say you're looking for a faint object, but you know that it's about 1.5 degrees from Epsilon star or something. So if you know your actual field of view, your true field of view, not your one that's on your eyepiece, you could take that field that you're looking at and say, okay, I'm actually looking at 0.5 of a field, so I need to move that field that I'm looking at 3 sections to the east, the west, or the north, depending on what object you were trying to find. Does that make sense?
You go back to your previous slide.
Yep. Yeah, so even 1.5 doesn't encompass the whole of the Andromeda, especially if you're doing it with photography. Photography will show you a lot more detail, right? You're soaking up way more photons than your eye can. But as he said, you can use a reducer, which in essence changes your length. That, speaking of fields of view, that's Clyde Tombaugh's statement. You have to have hope. Otherwise, I don't think you could handle it. Of course, you have to have both luck and pluck. That was a common saying back then. Pluck meaning perseverance, to stay at it, not to give up on it. And that is actually Clyde Tombaugh right here, working in the fields. Clyde Tombaugh, of course, the discoverer of Pluto. Sorry. Exit pupil. So the human eye goes roughly between the pupil will open up between 2 millimeters to about 7 millimeters. In some kids, it'll go 8 millimeters. A telescope, once you put your magnification in, brings out that image in millimeters. So if you're not dark adapted and you've got a 5 millimeter image coming out of your telescope, but your eye is only at 2 meters because there's a whole bunch of bright lights around, that most of that light's going to be bouncing off of your iris and going back and hitting the eyepiece. You're going to get little flashes and it's going to be uncomfortable, basically. So it's important to be dark adapted, but there are times when a small millimeter exit pupil is important. And for galaxies and deep sky, stuff like that, 2 to 3 seems to be the optimum, because your eye is probably about 5. I don't think mine would get any bigger than 5. As you age, your pupil will not dilate or become nowhere near as large as 7.
That's why most of the people look like Robbie.
Yep, exactly. I used to read my charts in my observatory with hardly a light on at all. And it irked me one night. I went out and I could not read those charts. It seemed like it happened like that. But speaking of this, so I was always told that 5 millimeter exit pupil is the optimum size to see the Horsehead Nebula. A beta filter or a UHC, an ultra high contrast filter, also help a whole bunch too. But for some reason, I was always told this 5 millimeter is the magic thing. So you got to figure out what magnification gives me that. Well, we can take my 6-inch here, my 150, and if I multiply it by 50, I only get a 3 millimeter. But if I use my 1500 millimeter long 300 12-inch telescope, 300 millimeter, if I put my 25 millimeter eyepiece in there, it gives me 60 times. I think that's on my next one here. Nope, just a minute. Just a minute. No, you're not supposed to see that yet. So if I wanted to, I never wrote that equation down here, but if you wanted to figure that out, you would take your 1500 and you would take the size of your aperture. You want to see the Horsehead. Take the size of your aperture. Mine was 300. And I needed a 5 millimeter exit pupil. So I divide 5 into 300. That says I need a 60 power eyepiece. Okay, now that I know that, my focal length is 1500. I divide it by 60 times because I want 60 power. Everybody still follow me? That means 25, right? 25 times 60 will give me my 300. I want a 25 millimeter eyepiece for the optimal eyepiece to go looking for the Horsehead. That'll give me a 5 millimeter exit pupil. This is the only time that would be important. Most people will just try an eyepiece. Oh, that's not a good picture. You'll try another one, right? And if you had pupils like that, resolving power, and this is a technical one for people who want to know really how good your telescope. You probably really don't want to know how good your telescope mirror really is, but it's a measure of your ability to distinguish small details. And the Dawes limit, Daw came up with this formula here. It is a mathematical formula, but it was done visually. And he calculated that if you took this is called resolving power, let's call it that. If you take 1/16 and divide it by the diameter of your mirror, that'll give you in arc seconds the smallest resolvable image you can see in your telescope. So for my 300 millimeter, I can see 0.3 arc seconds. And this is the limit at which when two stars become elongated enough that you think there are actually two stars there. And that's how he calculated all this.
Was it called the Dawes limit?
Yeah. Is that what I'm not saying? Did I not say
No, I'm not
Dawes?
hearing, but
Yeah.
I'm just curious.
Yeah. So what does that mean? Arc minutes. We don't even know what that means. So the sky's divided up into 24 hours. Okay, and in each of those hours, you got 360 degrees. So 1 degree equals 60 arc minutes. That's pretty straightforward. And 1 arc minute equals 60 arc seconds, just like we would expect to see. So the full moon, how big is the full moon? Anybody want to? It's a half a degree. So it's 30 arc minutes, just to give you a sense of size. It's about correct? 30 arc minutes is the moon. Unless it's a supermoon, might be 32. And this is just your rough scale. You can use your hands, like say 10 degrees, 25 degrees. 25 degrees is the size of the Big Dipper. That's pretty straightforward. Miser and Alcor are 12 arc seconds apart. So that is almost a quarter of the width of the moon, right? 0.5 or 0.15 would be the halfway point. So it's quite a distance. And you can split these with your naked eye. Of course, these are the two stars in the crook, in the bend of the handle that they used to use during the Roman times. If you could see those two stars, you had good eyesight, you're a soldier. And then let's get down to the Horsehead, or the Orion Nebula, sorry. This is way bigger than most people think it is. It's almost a full degree. So that would be 2 full moons in size. So you can't put a lot of magnification on here unless you're going in looking for the trapezium, the little small stars inside there that form the trapezoid. The double-double up in Lyra. So we got Epsilon Lyrae. The two stars themselves are 3.5 arc minutes apart. So if you can split those with your telescope, you've got down to 3.5 minutes, but we're talking arc seconds. So these smaller ones here are actually 2.5 and 2.2. So if you can split those, you're getting down to 2 arc seconds. Really, on my telescope, about 1 arc second is about the minimum I've ever seen. I could never get down to 0.3, but in theory, that would be the maximum I could do. So if you wanted to figure that out, that would be the equation to do that. And if you want more on this, it's in the handbook. Dr. Roy Bishop has it on page 49, telescope parameters. It's way more technical than what I went through here. But Roy was the observing handbook for 18, 20 years between 1982 and early 2000s. Sadly, he's still in good health and everything. He's not a little bit of dementia. I guess we all would hope to have just a little bit when we get a little older. So, anyway. Yeah, so eye relief means that point where it comes out of your telescope where you want your iris to be is farther away from the lens. In the old day, most new eyepieces have quite a long eye relief, so that people wearing glasses don't have to take them off or shove their eyes right up to it. A lot of them really cheap old eyepieces, you just have to put your eye almost right on top of the eyepiece to find it. So they are more comfortable. All of mine are long eye relief ones now. So, any other questions, or was that quite confusing? And that's it for that. Okay, how did everybody do with your Messiers last? Where's my Messiers? Anybody get them all? They were good. Yeah, excellent. Yeah, and they are all doable. They were all doable in binoculars last month. Supposedly, they're all within range of binoculars. The list of 110. Now we're going to run into the toughest one here this month, and we've got 5 objects this month. Not a big workload at all. Oh, I should go. So we're going to do M15. We had some great pictures of M15. You actually had all the pictures. You had M15, you had M2 in Aquarius, M72 in Aquarius, 73 in Aquarius, and then M30, you had that too down in Capricornus. And they're well placed this month for us. So let's start with the constellations. We got to be able to recognize Pegasus. That's quite an easy one with the big square up there that comes up with the neck and goes out to Epsilon out here, the nose. Aquarius. They always say Aquarius has this little Mercedes-Benz or Y-shaped asterism there. I find that star is dim, and it doesn't really pop out to you that. But once you know where the constellation is, you can recognize that. And if you can recognize that, then you know where Alpha, Beta, and then Epsilon is down in there, which you'll need to know. And Capricornus, of course, is our chevron-shaped constellation, about 10 degrees off the horizon. Okay, so our first target's M15, and that's pretty easy. You're going to come off of theta over to epsilon, and then you're going to go about half that distance, which is about 4 degrees over to M15. And you'll also notice when you're winding or going out there with your binoculars, you'll know there's a bright star right beside it. Makes it an easy one to find. M15, the great Perseus, the great Pegasus cluster, is a really bright object, easy in the binoculars. Our next object is M2, another great object. So we're into Aquarius here. Everybody sees that little asterism up there. I think I've got a little thing here. Yeah, they call it the steering wheel. Also, I've heard it called. So you're going to go between alpha and beta, and then you're just going to slide north a little bit. And then for 72 and 73, we're going to follow right down to epsilon, and it's not too far of a jump here. I got a better map that we're going to show for, they're pretty close to each other. Capricornus, we're going to jump from delta here down. I'm not sure what star is there, but we're going to jump over to a bright star and it'll be right beside it. And then this is another bright one too. These will be your toughest ones right here. Okay, so there's our M2, fairly easy, comes down, makes a nice little triangle. It's not really an isosceles triangle, but it's almost straight up. And I believe I wrote down the distances there. Aquarius, that's 5 degrees north. So if you put that in your finder scope, most finder scopes are about 4 degrees. That's going to put you almost to that edge of that, so you haven't got to come very far off it. And M2 is an interesting cluster. M15, I had a little tidbit here on each of these. Each of these clusters this month has a little something special about it. M15 is one of the oldest known globular clusters, between 12.5 and 13 billion years old. M2 is actually one of the largest known clusters, over 175 light years wide. Okay. And now to find these, there's a stick here. Now you could come down to the end star here, epsilon, and you could just try to jump down here, maybe find this star down in here. But I found it easier with my binoculars to jump back up to this star, jump over to here, and then start working my way down. And this was very obvious in my binoculars, this little triangle here. And then as I followed it through, I could see this bright star. That little star there was not as bright as it's shown on this map here, but you could see this little shape here. And once you found that one there, it was just within almost your field of view, 1 degree, about 1.5 degrees over M72. And M72 is one of the remotest of the Messier ones, at 55,000 light years away. So it's not going to be bright. It's a long ways away. M72, and then M73. I guess I got to go back just for a second. M73. Okay, this will be your toughest one in the binoculars. I could not get it in 10 by 50s. My 15 by 70s, I could get it, but only after I found it in the telescope and was able to find these two stars and said it must be there. And when I did, I could see a faint little star there. And it was at one time thought to be an open cluster for many years after it was discovered by Messier. But in fact, it is actually just a chance alignment of 4 stars. When you first see it in your telescope, you'll see 3 bright stars. This star here is a lot dimmer than what is shown on there. I don't know, maybe it varies a little bit. It might be a variable star, but I've never seen it real bright. And then down to M30, and down and over. And this is called the jellyfish cluster, or the spider glob, as I used to call it. but you can sort of see the tentacles hanging down, and it's very obvious in the telescope. You won't see those in your binoculars. But all these objects, barring M73, if you can get M73, you got a good chance to get all 110 in binoculars. Okay, and that ends that. We got one more little thing here. We do an asterism once. You aren't supposed to see the name of that. All right. I got rid of the Monty Python humor. And we went back to this here. So we are looking for Cassiopeia, which is up nice and high now. So we're going to try to find Cassiopeia. And we're going to take the sharp angle of the Wedic W, as I've heard it called by some. And we're going to follow it over here. And that'll give us to this house shape. And this puts us over towards the North Star over here. So this is Cepheus, the king. So we're going to try to find our way over here to find this side of this house. And here we are again, Calf. We're going to go over and find it there. Can anybody see the asterism yet? We're going to come down and we're going to look. This is a binocular object. It's a large object. It's just 2 degrees or more in size. So you're going to have to see it in binoculars. It's upside down there. One more. I have one more picture. Yeah, right there. So this is a close-up of it, and the field has been flipped here in my binoculars. That I have a mirror on my binoculars, so I can you don't have to hold your binoculars up. They go down like this, and they hit a mirror, and then the mirror aims up into the sky. So it's called the Lucky 7, and it's about 2 degrees in size. So. And that's an easy one to find in your binoculars. Have fun. Also, I suppose, while you're there, you could look for it. They call this the airplane. It's not real obvious, but it is known. In a telescope, probably you'd see that better than you would with your binoculars. Oh. And good night. Is there anything else anybody had? It's 9 o'clock. Yep.
Two quick questions about things I saw in the sky. And I was just like, I feel like I should know the answer, but I don't. But like one night when I was surprised, I was watching a satellite go, and then it kind of like got really bright for 2 or 3 seconds. Is that just like a sun reflection?
I'm going to let Don take that one. He's a big fan of the Iridium satellites.
Did you hear that? So I was just looking up at the sky the other night, looking at a satellite go by while I was waiting, and it just like started to shine really bright for just a couple of seconds, and then just dimmed back and continued.
Yeah, well, that would have a side to it.
Like it would have.
Yeah, and it would just have to turn enough sunlight from below the horizon on, but
yeah.
Just have to be like so it would make a trail where
yeah, okay. I just never seen that.
No, it still is a bit of a thing to go look for these iridium flares. They're called.
They're iridium flares.
Yeah, from the iridium constellation of satellites, and they were shiny. Supposedly, the new telescopes that Musk put up there were supposed to be dark. They're not dark. If you've we've seen evidence here tonight of you guys taking your pictures. I've seen some of them with like dozens of trails going through them. Yeah, terrible. But yes, it's actually quite spectacular to see. But
another thing I saw, which again I just wasn't sure what this was, but I was driving Majorville the other night, a week ago, and I saw like a green flame, a green flame with kind of like just like that sparky type tail, and that lasted about 7 seconds, like so low, and maybe like 5 seconds. Felt like.
Could it be a fuel dump?
Yeah.
Could it be aviation fuel?
Like a green flame, yeah. But it was just bigger than I'd seen before.
Yeah.
some meteors are iron. some have the nickel.
Okay.
I think it's the nickel that would give them the green. I see.
Cool.
How long did it persist, or how long did it last?
It, like, you know, it felt
Just-
like 7 seconds, but it was probably like 4.
Yeah,
It was probably about 4, and it was just like really slow.
yeah.
Because I'd seen one about 10 minutes before driving that was just, you know, orange and sparky, but this was like green and
Yeah.
good 4 seconds of
So-
you know.
To last that long, it would have had to been almost like a fireball or something broke off, and then I've seen them hang for a long time. And
Yeah. Yeah.
That's more likely.
what was?
Is it called bolide, B-O-L-I?
Yes,
Yeah.
a bolide. Yeah,
Yeah, I've seen some of them, you can see the smoke.
Yeah,
behind
yeah.
as well. They're slow.
Yeah. Yeah. Okay. Thank you.
Yep.
I was like, I need to ask about
no,
this
right.
place.
Okay, well,
One other little thing. If anybody's going to explore the universe, for the craters and everything on the moon, there's a really good moon globe HD iPhone.
Yeah.
It shows all the craters.
I'd like to,
The
yeah,
nice thing about it is you can mirror that north to south. West.
Yeah.
So it would match exactly. Comparing the two.
Yeah.
Okay.
Yep.
Just one comment. I did bring in a telescope.
Oh, yes.